All right, and welcome to another lecture. So today we're gonna look at analytic functions. So we're gonna do the definition. We're looking at the definition. That's subsection 241, and then we're gonna prove that analytic functions are complex differentiable. That is, they are holomorphic, right? They're actually infinitely complex differentiable. So that's section 242. All right. So what are analytic functions? Analytic functions are functions that have a convergent power series in every point. So if I have a function f defined on an open set U, then we say it is analytic, sometimes also complex analytic if you want to emphasize it, but for us we'll just use analytic. If for every p in U, so for every point in U, there is an R and a there's going to be a disk in U of some positive radius and a power series that converges to F, right? So around every point, there is a little disk and a power series that converges to F in that little disk, right? For every Z in that disk, it is F is equal to this series, right? And you're supposed to get this at every point. That's what an analytic function is. So eventually, we'll show that holomorphic functions are analytic. Today we're going to show actually the opposite. We're going to show that analytic functions are holomorphic. So one direction is a bit harder to prove. So we'll wait with that for later. Now, a subtle point that's actually also going to have to wait until we prove that holomorphic functions are analytic is that it's not immediately clear that if you have a convergent power series that it is analytic. Now why? Well, because just because I have a convergent power series, how do I know that it converges in some disk? So at the center of the disk, okay, I do have a neighborhood and a power series that converges to my function, which is defined by this power series. But what I don't know is if I look at a different point in that disk, if I can expand it, as a power series around there. Now, this could be done just looking at power series, but it's actually going to be easier once we have. So we're going to prove that analytic functions are holomorphic. We're going to prove that actually power series, just a single power series is going to define a holomorphic function. And therefore, once we prove that holomorphic functions are analytic, a little later on, we're automatically going to get that a power series is analytic, even though it seems like obviously that should be true. But it takes some work. All right. So what are we going to do? We're going to look at a function defined by a power series. So we're all going to look at just a function defined by a power series, not necessarily analytic at this point. It's going to turn out to be analytic, but not today. So we have some function defined by a power series. Then f is complex differentiable, and the derivative is actually a power series again, right? One way to write it is like this. And this is, at every z in R, and the convergence is the same, right? So the original guy converged in delta sub R, so in a disk of radius capital R, and the derivative also converges in a disk of radius R, right? And is a power series, right? Okay, so let's prove this. So without loss of generality, I'll just have PB 0. That's going to make, we just make these guys Z. That's going to make things easier. And it doesn't really matter, just it would make everything a bit messier, right? So we're going to differentiate a power series. Let's see how we would differentiate z to the n, right? One of the terms in the power series, right? Again, we're taking p equals 0, right? So z to the n, if we look at the difference quotient, well, this is just the geometric sum formula, right? So I'll let you work out why that's true, right? But that's true, right? So we can the numerator over here is divisible by the denominator, so that's kind of cool. There is no denominator, right? It is just a polynomial, right? And as z tends to z naught, then the difference quotient does tend to the thing that I want, just the power rule, right? So it's, well, I mean, this is basically showing that z to the n is differentiable and what the derivative is, right? Okay. So let's look at all of f, and let's suppose that we'll at this point let's look at 2 points in the disk, and let's look at the difference quotient of the entire series. So, well, we can add series, right? So just a little bit of messing around with this, and I get that the difference quotient sort of goes inside, right? So we have that this difference quotient is the sum of these guys, and we rewrite the difference quotient of Zn using the formula we just had before, right? And now we seem to be almost there. If we're trying to take the limit as z tends to z naught, because then this guy, the limit of that would be the right thing. We would get precisely the right sort of series here. Now, the problem is that if I put a limit out here, that limit is in front of this infinite series, right? So I need to swap those limits, right? This limit over here and the limit that I want to put in front of this of the difference quotient, z tends to z naught, right? So basically, I want to show that this thing is, I get a sort of continuity, right? That I can just plug the limit in there, right? I can just plug z naught for z in here, right? That's what I want. Right. So we're gonna do it by looking at a bunch of neighborhoods, right? So looking at a disk of radius r, capital R, is a little bit too much. It's also a little bit too much to look at something slightly smaller. So we're going to look at something slightly smaller than slightly smaller. We've seen this argument before. I mean, at this point, it might seem, well, we're talking about something slightly smaller and then slightly smaller, and that, why did we come up with two, S and R? Well, it will be clear in a little bit. And I copied the picture from before, so it still says P, but P is 0, right? And from now, let's suppose that Z naught and Z are in the S disk, just inside here. Now, because S is really arbitrary, Z naught can be really in anything in the big disk in the end. All right. So let's look at the inside over here, right? And let's look at the absolute value, right, of the inside. Now, if we're, if Z naught and Z are in this disk, right? So if I just use triangle inequality, I move everything inside, then these guys are just basically, I bound them by S to whatever power, right? And so then they're kind of the same thing, right? And I just get the power is just n minus 1, right? So I get, I still have this sum in there. This guy doesn't really depend on k. I'm not actually sure why I put it inside here, but I did. It's okay. But I have n of these, right? I go from k equals 0 to n minus 1, right? So the n comes out. So I just get this formula over here. So far, I haven't used the little r. No, to use the little r, well, I really want this guy in there, right? Well, actually, I'm really looking at Okay, the thing without the n, but just with the r, right? That's what I'm gonna know something about it. Just a number that's that's strictly less than big R, right? And so to put the little r here, I have to again divide it out here, and so I'm gonna have this formula over here, right? All right. Now, because the original series converged, then this guy is bounded. Actually, it's bound. I guess the proposition that we proved was that it had r to the n, but it doesn't really matter, right? It's just if the r to the n guy is bounded, this guy is bounded as well, right? Because f converged, and in this disk of radius capital R, I wouldn't be able to do it with capital R here. I need something smaller. But R, little r, is strictly less than capital R, right? So I have that this is a bounded sequence bounded by some m, right? So now I want to use root test, right? So I'm going to take the nth root of this thing, right? Which is just this thing, right? So it looks a little nasty, but it's not too bad. So I have this guy over here is bounded by m. That's where this m comes out. Then I have I have this n out here, and I have this guy, right, to the n minus 1's power, and I'm taking the nth root. Now, oops, that's not what I wanted. Sorry. So if I'm taking the nth root of the n, that goes to 1. The nth root of the m, yeah, that definitely goes to 1. And this s over r, so it's not quite to the nth power taking the nth root, but yeah, in the limit, that's like that's the same. So as n tends to infinity, this does go to s over r, and we picked a little s to be less than little r, so we get that this is strictly less than 1. So root test applies, and it says that this series converges. All right, and so what does that say, right? I mean, that says that right, because I could that was this thing was something that bounded this guy, right? So I have that that actually if I put in the sum over here, right, that thing converges, right? Because it's now by I guess comparison test was using this summing this guy, right? And that's this guy over here, that doesn't depend on z and z naught, right? I mean, so this is uniform, right? So z can move uniformly in this S disk, right? And so I have that this guy converges uniformly in this disk. All right. That's what I wanted. So now I can swap the limits, right? I can put the limit inside the series. All right. So therefore, I can take this series, right, that we wrote before, and I can take this limit and put it inside, meaning I can, right, inside it's really easy to take the limit. I just a polynomial, right? I just replace the z by z naught, and now this simplifies precisely to this, right? That's exactly what I wanted. And since S and R were arbitrary, right? So we could, if we had any z naught, we could choose an S and R that are, bigger than the modulus of z naught, right? All right. Now, a corollary of this, well, so one corollary of this is that a power series is holomorphic, right? Because it's complex differentiable, right? at every point, right? So power series are holomorphic. But it's actually more because the derivative is a power series again, right? So if I have a function defined by a power series, then it's infinitely complex differentiable. I can differentiate it, and then I can differentiate it again and again and again, right? The derivative is again differentiable because it's a power series, and that's all we needed to get complex differentiability here, right? And then you can write down what the formula is, right, for the kth derivative, right? Just by induction, right? And they all converge in the same disk, right? Now, there's another consequence of this, and that's okay. So if I take the kth derivative and I plug in p, if I plug in p, right? So this series starts at k, right? Because each derivative, kills the constant, right? So after k derivatives, I'm starting at index k. Now over there, once you're at k, this is the 0 power, right? So I just get the ck, right? With some with some mess in front of it, right? And all the other powers are 0, right? Because all the other, this z minus p to whatever power is, those are all 0, right? Because the n minus k is then bigger than 0, right? So therefore, I just get, I really get the kth derivative of f at p is n factorial, because that's what I'm gonna get out there, times the ck, right? Or I can solve and I get this formula, right? So I have a formula in terms of the derivative for the coefficient of the nth coefficient of the power series. So I can find the coefficients of the power series by differentiating the f. All right. Now, one consequence of that is that the power series is unique. Once I have a power series converging to a function, there can't be a different power series at the same point converging to the same function, right? Because I just need a little neighborhood around p, because all I need to take derivatives is a little neighborhood. Once I can take derivatives of this function, I know what the coefficients are. So I know the power series. So the power series is unique, right? And again, it only depends on the values of f in arbitrarily small neighborhood. I don't even need to know f very far out, right? For any sort of disk of radius epsilon, for epsilon being 1 over a million, that's fine. That's good enough. 1 over a trillion, right? So that's a consequence of this, right? Now, as far as analytic functions, we defined analytic functions, and we didn't really do anything with them so far. We were just talking about power series, and we said, well, and power series are not necessarily analytic. But if you have an analytic function that, in particular, it does have a power series, then an analytic function is infinitely complex differentiable. Now, because I can differentiate the power series at each point, right? I also find that the derivatives have power series, right? So an analytic function is infinitely complex differentiable, and each derivative is analytic, right? So the first derivative, second derivative, all the derivatives are analytic, right? And this is going to be the weird thing. In once we prove that holomorphic functions are actually analytic, then we're going to find that holomorphic functions, once you have holomorphic function is a function that possesses the first complex derivative, right? That I can differentiate at every point, right? Once we will prove that every holomorphic function is analytic, then it will immediately say that every holomorphic function is infinitely complex differentiable, right? and each derivative is holomorphic, right? So so suddenly we'll get sort of, this is sort of this feels to me like a really weird thing to say, right? Just because you have one derivative, suddenly you have infinitely many derivatives, right? But that's what it will turn out to be. All right, so so that will take a little bit more to prove that. So far we have this one direction. Analytic functions are holomorphic, and not just that, analytic functions are infinitely complex differentiable, right? And in particular, power series are holomorphic and infinitely complex differentiable, and their derivatives are power series again, right? So next time we're gonna look at we're gonna define the exponential using a power series instead of, we defined it before, giving an exact formula in terms of the real exponential and sine and cosine, but that's kind of maybe not as nice a definition. Maybe we want to a complex analysis definition. So a complex analysis definition of the exponential would be, we look at the power series, right? We define it in terms of a power series, right? So that's what we're going to do next time. So see you next time.